different tables, and my expectation is you will talk to me about what you got for your answers. However, I'll give you 2 minutes, maybe 3, maybe compare what you wrote down with somebody around you in case you didn't have a chance to do that on Friday, so that when I call out the table or call out you feel maybe a little more confident in your answer. So I'll let that happen now. All right, I'm gonna take back class, my turn. These notes, and there will be some definitions and vocabulary given out today. If you've been in AP Physics 1 before, you will know most of this vocabulary, but if you've never had a course of physics before, this is likely to be new. I would encourage you to begin your Unit 1 notes. And today, as we start, Unit 1 is kinematics. It is the study of motion. As a starting point, I'll remind us on Thursday, we began by talking about shared measurement. We dealt with the idea of an origin and a frame of reference. The idea being that we were going to have a shared set of experiences and we needed a shared way to communicate that information from one person to another. I want to extend that a little bit today with a brief reminder that there is a jargon to every science, maths, any study is going to have a jargon associated with it. The jargon is the language of that study. And for every study, the meanings of the words are not chosen arbitrarily. This is not a language class or a class of prose where we're going to be reading something and attempting to interpret what the author has communicated to us. This is a science class, and therefore the language we use is precise. It's not open for interpretation. Do we understand? So the choice of a word is important. And when I choose words, especially words related to your test questions, I will ask specific things, and my word choice is important. Do we understand? So we need to be careful about our word choice. So when I believe that you have a poor word choice, I'm not attacking you. I'm trying to tell you that the word choice you're going to need to use needs to be different to match the jargon of my class. You understand? Excellent. So let's begin. Which bike is ahead at 3 seconds? Bikini Bottom, why don't you tell me which bike is ahead at 3 seconds?
I said that bike 2 was ahead.
And why did you say bike 2 is ahead? What is your evidence?
Because at 6 seconds, 3 seconds, 3 seconds, the position is around 40 for bike 2 and like 25 for bike 1.
That's all reasonable. All good there? Anybody in your work say, or the person around you say that bike 2 is higher than bike 1? Is there anybody who said that? Okay, there are like 6 people in the other class. Any reason to believe bike 1 is, or bike 2 is higher? Higher on the graph, maybe? That's an inappropriate use of the word higher. What is the vertical axis representing? We're told what it represents in the question.
Position.
That's right. It says very clearly it's the position of the bikes. More importantly, it goes on to say that the vertical axis is in meters, correct? So we know quite a bit about the graph just from that. That suggests that the vertical axis is more like a numbered line, right? We have an identified 0, that's our origin, and the cyclists moved in a region of space where we observed them over 100 meters, right? That's the full range of the vertical axis. I don't think one bike was on top of the other. Do you? I can, in front of the other, at a position further away from the origin than the other. Precision of language is important. We tend to say higher because we tend to think of the top of our paper is up. But that's incorrect here. And do we all understand why? Excellent. Excellent. So let's go with Atlantis. Can you answer question number 2?
The bike which is ahead at 7 seconds, we said it was bike 1 because similarly to before, the vertical axis, like the position in meters for bike 1 is greater, with it being at around 64 to 65 meters, while bike 2 is at less than 60.
Excellent. Excellent. All fine. All fine. So can Pride Rock tell me what is happening at 6 seconds?
Both bikes are in about the same position.
I would even go as far as say they're at the exact same position, right? And it looks to me like they are right there at the same point in space. somewhere, what, a little past the 50? We all good with that? Maybe 55 meters away from the origin? Awesome. So let's go with Gotham. Are the bikes ever at the same speed?
I said no because it's linear. They're at a linear speed, so they're traveling at the same rate, or they're each traveling at their own rate for the whole graph.
All right, so I'm not taking any issue with your language directly, but let's handle this a little bit. He said it. He had something about the slopes. You guys heard that, right? Let's take a bit of an aside here for a moment. I want to talk to you about reading graphs and what we do when we start taking a look at a graph. I'm going to try and present you with as many possible graph-like situations as I can throughout the course of the year, which they will do on the exam too. Either they'll present you with graphs and ask for you to comment on them, or you'll have to sketch graphs, or you'll be given data. It's going to be some range of your capacity to utilize a graph. When presented with a graph, there's the obvious things that a graph tells you. This one we know is position and time. Right, that's clearly articulated to us in the scope of the problem, with them saying vertical axis indicates position in meters and horizontal axis time in seconds. Right, that's clearly stated in the problem. However, every graph also can be evaluated for the meaning of the slope and the meaning of the area of the graph. And although I will tell you what I think every graph is about, you could face a graph that I had not anticipated on the exam. And it'll be your responsibility to try and figure out what they're trying to communicate to you. So let's deal with a bit of a mnemonic. If you're faced with the graph and you want to see what information the graph might be telling you, I want you to evaluate the slope and I want you to evaluate the area. To evaluate the slope, I merely want you to create a fraction and put the units of the vertical axis on the top of that fraction and the units of the horizontal axis on the bottom of that fraction. So for us, the slope for this graph is meters on the top and seconds on the bottom. And then say it as it's meant to be said. That line means per. So meters per second. Do you know of any measurements that are related to meters per second? Yes, sir?
Speed.
I think speed is a word that seems to be related to meters per second. So you may or may not know what the units are trying to signal to you, but I don't think it's unreasonable when you get units that match something you know about to qualify it and say, I think this might be speed. This is evaluating a graph based on its units, the likely course of what it's trying to tell you. In fact, we can go further and talk about area too. If you're trying to test the area of a graph, for that, you take the first unit, the vertical, meters, and multiply by the second unit, which in this case, seconds. There's no per here, just to just be meter seconds. That's all you would say, meter seconds. Do you guys know any measurement that is meter seconds? Now, even if there is something that meter seconds might mean, if you don't know what it is, then the area has no meaning to you. You follow what I'm saying? Don't create something that's not there, but if you don't know what it is, then it doesn't have meaning to you. Now, we do this for every single graph. Every time we're faced with a graph, we evaluate what it tells us, and then we try to go further and talk about its slope and its area. However, as an aside, in your notes, as you're taking notes for Unit 1, every position versus time graph tells you speed. It is the slope of the graph. And although I'm not lying to you, I am leaving out something important. So let's continue this aside for just a minute. The word speed is different than the word velocity. You've probably used both words before, and you've probably heard both words before, but they do not mean the same thing. Speed is a scalar, and velocity is a vector. Scalars tell you less information. Scalar values are just what they say. They are a number. Vectors, however, are a more complicated value. They contain not only a scalar portion, their magnitude, but they also contain direction. So if I ask for a vector value, meaning if I ask you to tell me the velocity of an object, I am asking you to tell me more than one thing. You should be telling me not only how fast they're going, the magnitude, but also in what direction they're traveling. The word magnitude is what I will use on most tests. I'll ask you for the magnitude of something. And students have a difficult time with the word. You can replace magnitude with size, and that will be an equivalent statement. So if I ask for the magnitude of the velocity, or I ask for the size of the velocity, I am asking for the same thing. So in a test, if you're confused, scratch out the word magnitude, write the word size, and ask the question again. Because most of you know what the word size means. So, is it possible that you could determine from a graph whether it's telling us speed or velocity? What if I had a set of data points on this graph and they look like that? How would the motion of that cycle be different than the motion of the blue and red cycle? What's that? No, I don't think so. Yes, ma'am.
It's slowing down.
I don't think so. I already heard from you. I haven't heard from you. Go ahead.
It's moving in the opposite direction.
It's moving in the opposite direction. Would you guys agree with that statement? It's traveling towards the origin. So I look at the blue and red cycle, and they're traveling away from the origin. With every second that proceeds, they get further away from the origin. But when I look at the green one, with every second that goes on, it gets closer and closer to the origin. Do any of these cycles change their speed during the course of our observation? No. The slopes stay the same. Because the slopes stay the same, they never change their speed. It's just that the green one is traveling in the other direction. So it seems clear to me that the slope of these graphs is the vector value, is velocity, not speed. Do you see what I'm saying here? So the slope of any position versus time graph is velocity. It gives you how fast the object's going and in what direction. For one-dimensional motion, right? I'm being very clear here. These objects are traveling in one dimension, a straight track. Right? We will get to two-dimensional motion, but a graph like this may not be able to give us two-dimensional motion. All right? You see why that might be true? Okay. All right. Although there's stuff here I do want to go into more. The truth is we have limited time today. So I would like us to do number 8, because I think we've handled most of the other portions. So let's talk about number 8. Who believes they have a model for the blue cycle? Okay. Who believes they have a model for the red cycle? I want to take issue with your models. So let's talk a little bit about models. What kind of functions are these? Linear. They are linear, right? What is the basic linear function? All right, so that's good. I'm glad you guys have that. Y equals mx plus b. This is the basic linear function. However, you guys have probably heard of other linear functions before, right? Like point slope formula or point formula and all that garbage. This is the most important one because this is a functional relationship. This is the one that we will use in here as the basic linear function. However, we need to translate this. So if your model has y's and x's in it, it's wrong. Our model has to represent what we see on this graph. What is actually plotted on the vertical axis?
Meters.
Not m meters. M would be the units of what's plotted. What is being plotted? Position. We need a symbol for position. And you're not going to like this, but the oftentimes used symbol for position is x, especially for one-dimensional motion. That's very common. You could say d for distance, but it's not distance being plotted, It's position. It's where the object is. What's being plotted on the horizontal axis? Time. What do you think? T, yeah. Lowercase t. Please don't use an uppercase t. Uppercase t is reserved for something else. What does M stand for? Nope. What does the M here stand for? Slope. So my expectation is we take a look at we'll use the blue one. Find the slope of the blue line first. I think the object goes from 0 to 90 in 10 seconds and is linear, so I think we have 9 as our slope. You do not have to put the units in your model. They tend to be distracting, especially if people start seeing them as maybe other variables and not the units. What does B represent? The y-intercept, which in this problem is 0. Are we good? So if I asked for bike number 2, you guys are good for that? Not particularly hard here. This is the mathematical model that describes the motion of the bike. Now, the question asked for you now to figure out where the bikes were at the 16-second mark. Do you know how to use the model to figure that out? Just put 16 in for t? All right, good. Not a problem. So, speed, velocity, vector, scalar, origin, linear graphs. We all good here? I need a small aside here. We have 2 words that are modifiers that will come up. These are modifiers. They can be used to describe speed or velocity. If I don't say it and I just ask for the velocity, instantaneous is implied. If I ask for speed, instantaneous is implied. Instantaneous means at a moment, at a specific moment. That's what instantaneous means. Average, unfortunately, has a very different meaning. When I say average speed, it is a different measurement than average velocity. They are calculated differently. I don't spend much time, nor do I test much on these, but because they have specific definitions, I want you to know what they are. Average speed is total distance traveled divided by the time interval. While average velocity is total displacement divided by the time interval. How many of you came to school today from your home? How many are likely to return to your home this evening? Okay, so most of you are going to have a displacement of 0 today, right, relative to the Earth. Don't tell me, yes, the Earth has moved. I get it, but that's not really functionally related to this problem. So you will probably have an average velocity of 0 because your total displacement over the course of the day is going to be 0. Does that really tell us what you did today? No, not really. So its functional use is probably small in dealing with what happened your entire day. On the other hand, if you live 10 miles away from the school, you'll probably travel a minimum distance of 20 miles today, right? 10 to get here, 10 to go home. So your average speed would probably take that 20 miles into account. You follow where I'm going with this? So average speed, average velocity tell us different things, but they have specific definitions. And we may be able to figure out average speed and average velocity from a graph. And sometimes they could be the same thing. I think if we look at these 2 graphs, the average speed for the blue one and the average velocity for the blue one will probably be the same because the distance traveled and the displacement of the cycle is probably the same. But we need to be careful. If something traveled forwards and then traveled backwards, its distance and displacement would be different. We all good? We'll look at examples of that in a bit. Let's go here. So could somebody, I'll pick a table here. We have not heard from, I don't know, let's hear from the Axiom. Somebody at the table there. Can you answer the question, describe the difference in the motion of the two bikes?
I say that bike one has a constant linear motion and that the bike two has an exponential rate motion.
All right. How many of you agree that bike one appears to have a linear function that describes its motion? I completely concur. And I think that that's super reasonable and super clear. So, bike one. How do you use the word exponential to describe bike two? I'm curious. Okay. Pretty common. I don't think bike two has exponential motion. Let's be careful with our vocabulary. Exponential motion specifically means that the position of the bike is related to e to the t, and probably some modifier before and after. Does it make sense that a person who is pedaling a bicycle could increase their speed exponentially over time? No, it does not. Exponential growth is a special kind of growth. It is related to the idea that the slope grows at the same rate that the function grows. So exponential growth means that they're getting faster at getting faster all the time. That's unlikely. There are lots of functions that increase their slope. Can you name another function whose slope increases? Yep. The quadratic function increases. The cube function increases. The quad function increases, right? All of these have an increasing slope under some condition. Just to say something's exponential is saying it's to the e power. I just don't think that that's what you meant. But we tend to say it for any function whose slope is increasing. I think all we can really say about this is that bike number two has an increasing slope. Their speed is not constant. Their velocity is not constant. In fact, I would argue that you could easily state that the velocity of bike two, is it increasing or decreasing? I think the velocity of bike two is increasing. The line is getting more and more steep in the positive direction. In fact, if we look at it, just apply your rules. You guys have rules for this from your algebra class. That appears to be the slope there towards the end, wouldn't you agree? And I go down, oops, didn't mean to do that. If I come down here to the bottom, is that a good slope for down there? So, be better than that. So would this look like we have a clear increase in slope over time? Yeah, I think so too. So the bike is getting faster. Is the blue bike getting faster? No. Now, somebody used the word earlier today, so let's go ahead and hear it again. If something's velocity is changing, what do we say is happening to the object? It's accelerating. That is a specific word. And I want you to know this word. So let's introduce it now and talk about it as a definition because it's important here. The word accelerate. You are not going to be happy with this. And I don't care. You have to know it anyways. The word accelerate or acceleration, by definition, is the rate of change of velocity. That's what acceleration stands for, the rate of change of velocity. It is how fast the velocity changes. Now, a positive acceleration means that the velocity is becoming more positive. And a negative acceleration means the velocity is becoming more negative. I'm being incredibly careful about my word choice here. I'm going to say this again. A positive velocity means the velocity is becoming more positive. A positive acceleration means the velocity is becoming more positive. And a negative acceleration means the velocity is becoming more negative. It does not mean speeding up or slowing down. We need to be incredibly careful here. I will never use the word decelerate. I will never use that word in here. I will always be careful. The word decelerate to you always means slows down. But tomorrow when we challenge this, you'll see why I want you to be careful about your word choice when it comes to acceleration. All right, that's enough for today. Have an excellent afternoon, yes. That goes online. That goes online. I can unlock it for you if you send me a message, but I don't collect it.